So zkEVMs, all right? So it's like, what's wrong with those? We've had already a bunch of those, like, last year. And what can be improved, what should be improved, and how do you, well, it's like everybody's trying to cheapen everything here. I mean, like Lambda class folks are trying to cheapen verification. It's like, and for zkEVMs, what also important is not only verification, but also the size of a circuit, and the proof generation costs are also important. So, I mean, we're going to talk about what can be improved. It's like how it is possible, and and what the hell does that mean? Compiled zkEVM. Let's go. What's wrong with those? First of all, just a little bit of preliminaries. Background. What's wrong with those? Vitalik told us, I don't know, it's like a year and a half ago already. It's like that, the biggest problem, which is like the biggest problem which we will face with all those ZK rollups is that, if something goes south, if a circuit goes, if a circuit goes south, right? If a circuit security goes south, and we're going to be able to, I don't know, mess with users' funds on L2s. So that's, and everybody who, and guess what? That's what happened. So it's like, this is, I know that this is a little bit like, old news. This is a little bit like, maybe might be not even, directly circuit related issue. Not only, it's like this, like there were issues, but it's like not only circuit related issue. But we've already faced the first exploit of zkEVMs, and I have a good feeling that it's not going to be the last one. So, meanwhile, auditability. It's like, you wrote the zkEVM, you're good, you're cool. I mean, you spent 2 years doing that, all right? And incredible amount of efforts, incredible teams doing that. And you're like, well, okay, let's audit those. Let's take a look what's going on. Well, let's say, imagine you did it with some ZK DSL, aka whatever, PLONK-2, PLONK-3, whatever people use right now, Halo 2, anything, all right? So, and imagine you did it. You resulted in a big chunk of code which only certain team can read, or only only specific teams can read, and you result into necessity to audit that, and that's what it results into usually. So, upgradability. I mean, if we're talking about Type-1 zkEVMs, right? Then each time something changes, or each time the protocol changes, or each time, I don't know, anything changes, I mean, you got to be required to redo a certain part of a circuit, if not the whole circuit. I mean, for example, just like it happened with, as far as I remember, PSC solution. It's like they've done tremendous job. It's like it actually works, and like the first Type-1 zkEVM, and that's cool. But the problem is that the gas limit proved within the circuit was quite low. So recent publication by Scroll and PSC folks shows that there are improvements to be made, and these improvements require circuit to be upgraded heavily. So that's also an issue with current zkEVMs. And compatibility. If we're talking about, again, Type-1 zkEVMs, and this is just like fancy number which I've put up there just to show how much of EAPs affect EVM behavior, and if any of those gets accepted, that's going to be an interesting situation. You're going to need to redo the circuit, and again re-audit, and again one more exploit, and again, like all that cycle. So yeah, how to avoid all that? I mean, because all of these issues will eventually result into people simply not trusting ZK rollups in general. So I mean, because there are always issues with circuits, you got to redo them, re-audit them. They're always being exploited, yada yada. And if we want for ZK rollups to be the end game, as like everybody tries to say, then we got to do something with it. So can we do better? And yes, we can. I mean, we can improve these things if we compile the circuit. I mean, this particular slide obviously mentions this like zkLLVM because it's null thing, and because we do it this way. But I'm trying to say that it's not only this way which is possible. So what does it get us? So it gets us, well, an improvement in security. It's like it gets us an improvement in security. I mean, it's like you get the auditable circuits, you get the circuits compiled from at least some kind of version of production grade EVM. We, for example, started patching EVM1, and an initial version was compiled from EVM1, and now we're working towards making it more performant, like suitable for that. Upgradability. I mean, yeah, EVM changes, pull the changes, get your whatever Rust CDP code, recompile it, you're good. So compatibility. I mean, yeah, how much more compatible this could be? I mean, even if you compile the actual EVM implementation. Yeah, I mean, this is just mentions that we use it ourselves. Performance. Yeah, it's like this is kind of if you do this with a circuit compiler, and I would encourage people to do this with a circuit compiler, then I mean, you gotta avoid those overheads you get with whatever is improving zkEVM, right? And no matter recent achievements reduce that overhead, but some time ago we have published quite an extensive report with runtime verification guys about about how much of a difference it makes to prove things via zkEVM or to generate circuits via a circuit compiler. And guess what? Difference between some general purpose zkEVM was about 20 times. So it's like zkEVM still have a way to go. So reinterpreting this EVM code via the general purpose zkEVM is kind of might be not the most economically viable way to do this. And the proof system, yes, it's like we kind of try to explore the. I mean, since zkLLVM is built upon a placeholder proof system, it's kind of became at this point more like a framework for proof systems than the proof system itself. But we will get into that later. What does it get us, and why we're doing it, and why we're doing it using our own thing. So yeah, secure circuits, EVM1. I mean, get it compiled. Might be not the best performance out of the box, but gradual patches, gradual improvements, improvements to the circuit generator. We get it. Auditability. Yes, I mean just for us all to understand, right? Like on the right, we can see the the beginning of a circuit, of a key-chack circuit defined on like with PSC within PSC design, and that's just the beginning. And you see, it's already goddamn it, 500 lines or something, and there are more a couple of hundred lines later to that, and it's What would you prefer to audit if you were an auditor? Would you prefer to audit the thing on the right, or would you prefer to audit the thing on the left, which is the key-chack implementation from within EVM1? I mean, of course, you'd prefer the left one, and yes, of course, there are inline calls and yada yada, but whatever. Still, it's still better. So upgradability. I didn't know which picture to put in here, so I just put the same one. Yeah, key-chack changes, recompile it, you get the circuit out of the box, recompiled it. I mean, cool. I don't know, key-chack changes, or not the key-chack changes, whatever, just random circuit changes, right? You gotta redo the whole thing. Please don't do it. Same thing. It's different points, same picture. Again, it's how much more compatible you can be if you generate the circuit from the actual EVM. Type-1 compatibility, and you're good. Type-1 compatibility, and you're good. Yeah, I mean, shit. Okay, well, it's a little bit weird. Basically, the size of a circuit, it's we target this to be with. I mean, both of these circuits mentioned are very large ones, right? I mean, it's just disclaimer, but we target for the zkEVM compiled and built this way to have as small overhead as possible over manually written circuits. We think that 10-15% difference is doable, but that's going to require us to do a lot of work, and currently we're on it. A lot of manual circuit generator improvements, a lot of manual circuits and everything, but that's doable. So the future, so it's the future when we don't build zkEVMs manually. I mean, shouldn't be that far away, I would say. Proof systems. Don't take this seriously. I just put together some whatever We'll dive into this. In the next slides. But in general, yes, like the proof system we try to use is, I mean, like, yes, it's obviously Plonkish factorization. The protostar-like approach for zkEVMs is being used within the first layer of recursion, because I mean that makes sense, right? So I know it's a little bit cringe, but anything to talk about, you know, like using lasso approach or something these days, but I wasn't able to change my slides fast enough, so I'll just skip it. And so that's what it is. Why placeholder? I mean, it's like, what's the nuances? It's like, what are you know, like trade-offs and benefits we're trying to squeeze out of this? So, I mean, the life cycle of such a proof system framework is kind of like, you know, known, right? It's I mean, very traditional one, very usual one. Modularity, yes. I mean, we kind of since we built it initially to be a foundation for the circuit compiler, we resulted into such a proof system to be, you know, quite flexible and configurable. So one can change the field over which circuit is being generated. One can field, it's like one can, you know, append new lookup techniques or like these kind of things. General recursion support, I mean, we do that by compiler as well. And yeah. So what are the trust assumptions of this, and what are we using for zkEVM itself? I mean, by default, of course, we use polylist polynomial commitment scheme, hash-based commitment scheme, no trusted setup, yada yada, all that thing. KZG is being used for zkEVM. I mean, it's like, it's an option we've appended quite recently, and for the zkEVM itself, we target to use this modification of proof system over KZG, obviously. Parameters. I mean, by default fields over which the whole zkEVM operated were Paulus fields, like Paulus Vesta curves, effectively. And I mean, but let's be honest, we're experimenting with different curves, and I mean, luckily we're able to swap those and switch those quite, you know, painlessly, I would say. So yeah, there are nuances. So what are the like, you know, lookup techniques we have put and we are putting into the compiler, into zkEVM? Ah, shit, no, they put lots of it in here anyway. Anyway, all right. So, so yeah, different lookup. It's like different lookup techniques are kind of available. We use for the opcodes. Yes, we are considering to, you know, simply, you know, it's like for the opcodes, for proving opcodes, we are considering to increase the circuit density by, you know, like either solving the optimization task, I mean, function optimization task, circuit density optimization task, or, I mean, that's how usually it's being done, or I mean, might be possible to increase this density right away. I mean, like kind of to introduce a discontinuation into the function of the density of the circuit density, and to get all the opcodes proven right away with lasso. We'll see what makes sense more, because I mean, sometimes it doesn't make sense. Yeah, so gate generation techniques. Yes, I mean, kind of VR quantization by default is, you know, Plonkish with custom gates. It's still kind of what is called true Plonk. For the first layer of recursion, as I already mentioned, we use a kind of protostar-like approach. And let's go next. We don't have a lot of time. Yes, it's like hash input, direct input. Also, yes, we don't have a lot of time, to be honest. Handwritten circuits. So yeah, I mean, it's effectively the point of discussion. It's if you should write a zkEVM manually, or you gotta try to generate those, and you gotta try to, you know, do something with it. So the trade-offs are, I mean, yes, of course, you get a better assignment table, you get In the same time, the downside of this is you get to define a lot of manual circuits via some zkDSL, zkLVM circuits. Yes, you get more sparse assignment table, at least for now. That is true. It's like, we'll get to this in the next slides. Does it reduce the design and development time? Yes. the result not always is performant enough, or like very performant enough right away out of the box, but like manual optimizations, and it's still cheaper and it's still faster than spending 2 years on writing zkEVM, which gets hacked after that. So yeah, I mean, it's like, what's the circuit generator process? Like what actually matters during the circuit generation for the zkEVM, and like, you know, in general. Yes, you gotta just choose the dimensions of the table you use. You gotta choose the dimension you use. You gotta choose the lookup option. Was like the lookup you want to use. It's like total amount of gates. Why it's important? So it's like usually you get, for example, let's say we have Poseidon, we have multiplication and inversion. Poseidon, and like, let's say you've placed it this way. Multiplication, you placed it this way. Like addition, you placed it this way, right? So for example, that's a naive circuit generation. You placed it like, you know, more subtraction, inversion, empty. You're not using the whole table. So what's important is to, like, we can also try the compressed approach. We can try to, like, you know, put them this way in a table. Still empty. We're still failing. Yeah, I mean, we're still failing. And flexible circuits, flexible gates. This is we kind of call it within the zkLVM, and we try to employ it to build the zkEVM circuit. So there's a metric function which you know, adapts the circuit dimensions to what you need, to the curve you need, and things like this. So this results in something like this. You get this, and I mean, perfect. So it's like you packed it as dense as possible. Yeah, it's like I was running out of time a little bit, but like, here we go. Questions?
Thank you. Yes, Misha, we got one question for you.
Yeah, so I am surprised by the choice of using it's like the LLVM suite. If I understand correctly, you are working at the LLVM higher level. And it seems to me that it is standing in a twilight zone where you cannot really target very specific optimization, because this is a relatively let's say generalistic language, but at the same time you cannot leverage either the highest level optimization, because you're not working with a very expressive programming language. So why didn't you choose to target, for instance, relatively modestly simple CPU architecture like RISC, Spark, MIPS, or an earlier ARM version?
Oh,